Hey everyone, Arturo here. Today's technical solo is about one theme that keeps showing up from different angles. Once agents leave the demo room and start touching production workflows, the hard part is no longer just prompting them, the hard part becomes operating them. I have 10 stories that I have found from different sources. I will share the sources for all of them, and they will orbit around the same topic: the engineering gravity well, observability, evaluation, security boundaries, shared memory, workflow orchestration, and model selection. I'll keep the facts tied to the selected sources, and I call out when I am moving away from the source fact into my own engineering interpretation. So, facts first, interpretation second, tranquilo but rigorous. The shape of the episode is as follows. First, how agents observability differs from classic software monitoring. Then, how data-aware agents at OpenAI depend on context, memory, and evals. Then, Microsoft's security framing for agent execution on Windows. And after that, we move into evaluation-driven development. Debugging, reasoning instead of stack traces, benchmark sharing, multi-agent engineering systems, Stack Overflow's agent-facing knowledge exchange, Mondays.com Day Zero Eval strategy, and finally, model evaluation for fine-tuned open source systems. Let's get into it. Our first article comes from the LangChange blog. It's called Agent Observability, How to Monitor and Evaluate LLM Agents in Production. Okay, the fact layer. The LangChange source opens with a pretty blunt claim. You cannot monitor agents like traditional software. The reason is not just that agents are AI in the vague marketing sense. The source gives three concrete differences. First, natural language input creates a boundary space of possible queries. Second, large language models are sensitive to subtle prompt variations and can produce different outputs for the same input. This means they are not deterministic. Third, agents make decisions through multi-step reasoning chains, tool calls, and retrieval operations that are hard to fully anticipate during the development. The article contrasts this with traditional software, where users often move through more predetermined paths. They click on buttons, they fill out forms, they navigate defined flows. It says a traditional test suite might cover 80 to 90% of code paths, and monitoring tools track things like error rates, response times, database queries, stack traces, and logs. For agents, the source says quality lives in the conversations themselves, and production traces become the foundation for continuous improvement. Our interpretation is that, for architects, this is a control plane shift. In classical web systems, observability starts from services, endpoints, queues, and databases. With AI agents, those still matter, but they are not sufficient. The unit you care about becomes the entire episode of behavior: user input, model response, tool choice, context retrieval, intermediate reasoning-like steps where visible, final answer, and user impact. That changes what you store. It changes your retention policies. It changes how you debug incidents. If an agent produces a bad support answer, the relevant question is not only, did the API return 200? It becomes, what context did the agent see? Which tool did it call? Did retrieval bring back the wrong document? Did the instrument hierarchy create a conflict? Did a small wording difference route the system down a bad path? My read is that production agent systems need observability designed as product telemetry and behavioral telemetry at the same time. The source does not provide an implementation checklist in the selected excerpt, so I will not invent one. But the architectural consequence is clear. If your traces do not capture the conversation and the steps that produced the outcome, you probably cannot evaluate the real system after that. Remember, what gets measured gets managed. The second article I found really interesting comes from my InfoQ. It's a presentation transcript. The title of the presentation is AI Agents to Make Sense of Data at OpenAI. Bonnie Xu from OpenAI's data productivity team describes AI agents deployed to help teams answer data questions. The example in the source is willingly very simple sounding. A business lead asks, how many ChatGPT Pro users do we have in Italy? According to the transcript excerpt, getting the answer is hard because the team may not know what table to use. The example path includes a data scientist, another engineer, 3 code deep dives, 2 quick meetings, and 5 Slack threads before finally getting an answer. The source names 3 takeaways: the importance of the right data context, the importance of memory for self-learning, and the importance of evals to make sure the model does not regress. It also states that at OpenAI, 80% of the company directly uses the data platform. And what is my interpretation about this story? Well, this story is about the hidden cost of institutional context. A question can be syntactically simple and operationally expensive. The hard part is not counting rows. The hard part is knowing which rows in which table, with which definition, and with which freshness level, and under which business semantics. For an enterprise data agent, the architecture has to answer 2 categories of questions. First, what does the model know at the moment of the query? That is the context problem. And second, what does the system learn from repeated interactions, corrections, and successful paths? That is the memory problem. Then, the eval question sits underneath both. When you improve context or memory, how do you know you did not regress on earlier data questions? The architect level consequence is that a data agent is not just a natural language to SQL wrapper. The article does not say natural language to SQL, so I am using that only as comparison, not as a fact claim about the system. The broader point is that the agent has to operate inside a map of data assets and organizational meaning. Without that map, it can be very confident and still waste everyone's time. I also read the 80% data platform usage fact as a scale warning. If most of a company uses the data platform directly, then agent mistakes do not stay in a lab corner. They become shared productivity failures across the company, or across 80% of the company. A brittle data agent can generate wrong answers, but it can also generate more meetings, more code archaeology, and more human cleanup. So the engineering bar is not just answer generation, it is reducing the coordination cost around data questions. The next article I found very interesting is also from InfoQ News, and it's called Windows Platform Security and the Race to Secure AI Agents. Here are the facts. Microsoft positions Windows as a trustworthy operating system for autonomous agents and introduces the Microsoft Execution Containers SDK as central to that strategy. The source says Microsoft argues that containment, identity, and manageability must be built into the operating system so that agents can be deployed and governed safely and at scale. The article describes the SDK as a policy-driven execution layer for agents on Windows and Windows subsystem for Linux. Developers can describe what an agent may access using JSON or a TypeScript SDK. Windows then uses process isolation for containment and session isolation when agents need separate desktops and identities. The article also mentions planned support for micro virtual machines for higher risk work, Linux containers for Linux-dependent toolchains, and upcoming integration into Windows 365. Which is super cool because basically it will allow agents to run some workloads on cloud PCs. The article also says IT teams are intended to manage the SDK policies centrally using Entra ID and Intune, while Defender and Purview provide the protection, observability, and an audit trail of agent behavior. What I see in this is that the operating system layer is waking up to agents. The question is no longer, can an agent call a tool? Can my agent invoke an MCP? Can my agent retrieve data? The question becomes under what identity, in what execution boundary, with what access policy, and with what auditability. That matters a lot because agents collapse the distance between intent and action. A human asks for a task, the agent might open files, run commands, browse systems, or manipulate resources. If all of that happens under a broad user session with vague permissions, then the agent inherits too much ambient authority. The Microsoft framing, as represented in the selected article, is that agent execution needs policy, containment, identity, and to be managed much closer to the OS. There is a nuance here. The article uses both current and planned language. Process isolation and session isolation are described as part of the mechanism. Micro VM support, Linux containers, and Windows 365 integration are described as planned or coming. So we should not treat every item as already generally available. We have to be careful with this. Architecturally, the big takeaway is that agent security is becoming a substrate of the problem. App-level guardrails are necessary, yes, but they are not enough. If agents are going to run workloads across desktops, cloud PCs, the WSL, and enterprise managed identities, the enforcement layer needs to be more durable than a prompt. Policy has to survive model variance. Audit has to survive user confusion. And containment has to assume the agent might do something unexpected, because that is the whole theme of today's episode. The next article is called Iterating Towards LLM Reliability with Evaluation-Driven Development. It comes from the LangChange blog, and it is an editor's choice, actually. It is written by the company developing Dosu. Dosu is an AI coding assistant. Basically, the post is saying that production-grade LLM products are hard because reliability is critical, but the product is underpinned by probabilistic functions. Dosu is described as an AI teammate that helps develop, maintain, and support software projects. The article connects Dosu's origin to the burden of open source maintenance, where maintainers or developers can spend too much time on support instead of new features. It also mentions maintainer burnout and issue bankruptcy, described as closing all open issues and pull requests. The article says Dosu continuously iterates on its product and needs to understand the impact of every change on end users. It uses evaluation-driven development, or EDD, to ship with confidence. The article also says Langsmith helped Dosu scale EDD by making it easier to monitor and search Dosu's activity. What I see from this article, I will say that the key phrase here is every change. In deterministic software, you can often reason about a change by reading the diff, running unit tests, and checking integration paths. In an LLM product, a small change to a prompt, retrieval strategy, or model version, the tool description, or even the routing rule can shift the behavior across cases you did not anticipate. Evaluation-driven development treats evals as part of the development loop. It is not a final compliance ceremony. For architects, that means eval sets become product assets. They are not throwaway notebooks. They are closer to regression suites, but with the important caveat that the thing being tested can be probabilistic and change its behavior. The Dosu article basically is useful because the product domain is software maintenance. That means the agent is operating near code, issues, pull requests, and developer support workflows. If it gives a wrong answer, the cost might be wasted maintainer time or bad guidance to contributors. The article does not quantify Dosu's outcomes, so I will not add numbers, but I think it clearly frames EDD as a way to understand user impact before shipping changes. My engineering read is that teams should expect eval suites to evolve like code. The cases that matter today might not cover tomorrow's failure modes. Production monitoring can reveal new examples. Those examples can become eval data. Eval results can guide future changes. This creates a loop: observe, curate, evaluate, ship, and observe again. Simple to say, hard to institutionalize, but that loop is where reliability starts to become operational instead of inspirational. The next one is actually a guide from the LangChange blog, and it's called How to Debug and Evaluate AI Agents with Observability. This LangChange guide says you cannot build reliable agents without understanding how they reason, and you cannot validate improvements without systematic evaluation. It's too long, didn't read. Says you do not know what agents will do until you run them. Agent observability is different and more important than software observability. Agents often do complex, open-ended tasks, so evaluating them is different from evaluating software. And traces document where agent behavior emerges, which means they power evaluation in many ways. This guide gives a concrete shape of failure. An agent might take 200 steps over 2 minutes to complete the task and make a mistake somewhere along the way. In that case, there is no stack trace because no line of code necessarily failed. What failed was the agent's reasoning. This guide also says developers still write code defining which tools exist and what data is available, and they write prompts and tool descriptions to guide behavior. My interpretation is the following. This is the debugging mindset shift. With classic software, failure localization often means finding the component, line, the query, or deployment that caused the problem. With agents, the bug might be distributed across the trajectory. The wrong answer could be caused by an early tool call, a missing retrieved document, an ambiguous prompt, a poor intermediate assumption, or a final synthesis error. This guide also says reasoning, and I am going to be careful with that word. We do not need to claim that the model reasons like a person. We are not going to get into that debate. But operationally, reasoning here means that visible or traceable sequence of decisions and intermediate behaviors that led to the output. If your trace only stores the final output, you lose the path. And if you lose the path, you cannot tell whether the problem was tool selection, context, instruction, retrieval, or model behavior. For architecture, this pushes teams towards granular evaluation. You might need to evaluate the final answer, but also tool call, correctness, retrieval, relevance, step ordering, and task completion. The guide says traces power evaluation at multiple granularities. That is the important part. This also changes incident review. A bad agent should not be treated as an embarrassing transcript to delete. It should become a learning object. What did the agent see? What did it do? Where did the behavior diverge from expectations? Can that run become a regression case? If the answer is yes, then observability and evaluation are no longer separate disciplines. They become two sides of the same production loop. The next one is about benchmarking, and it comes also from the Line Change blog. It's called Sharing Langsmith Benchmarks. This article is basically saying that the biggest pain point the company hears from developers taking apps into production is testing and evaluation. It says this pain is sharper because of a constant stream of new models, retrieval techniques, agent types, and cognitive architectures. Langsmith is described as adding ways to share evaluation datasets and results, with the goal of enabling community-driven evaluation and benchmarking. The article also mentions a new line change benchmarks package for reproducing results and experimenting with architecture. A key fact, the article says, test sharing publishes data and metrics showing how different architectures perform on the same tasks. It also says each evaluation result includes full accompanying traces, not just final results. So users can inspect step-by-step execution of different systems on the same data point. The first benchmark mentioned is a Q&A dataset over the line change Python docs, where answering questions requires synthesizing answers from different documents in a logical way. What I interpret from this article basically is that this story is about moving evaluation from isolated anecdotes towards reproducible comparison. If every team tests its own agents on private examples, you can learn locally, but you cannot easily compare approaches. Share benchmarking help create a common surface for discussion at an enterprise level. But I think the article's trace detail is the most architecturally important part. Aggregate metrics can tell you that architecture A scored higher than architecture B. Traces can show you why. Did one system retrieve better documents? Did another take unnecessary steps? Did one synthesize across documents more coherently? Did one fail in a way that would be unacceptable for your product, even if it is average scored looks fine? For technical leaders, that means benchmark systems should not only rank models or change, they should expose execution. A leaderboard without traces is like a production dashboard without logs. May be useful, but not enough for diagnosis when things go wrong. There is also a governance angle and interpretation. When teams argue about switching models or retrieving strategies, shared datasets and comparable traces can lower the temperature. Instead of my demo felt better, the conversation can become on this dataset, with these traces, under this metric, here is what changed. That does not eliminate judgment, but it gives judgment something solid to stand on. The caution is that a benchmark is never the whole product. The selected source itself frames the first benchmark around Q&A over line change Python docs. That is useful for that task shape, not proof that an architecture is best for every domain. So the mature move is to use shared benchmarks as a reference point. Then build domain-specific evals around your own production traces. The following article comes from Cisco. It is called Agentic-Engineering: How Swarms of AI Agents Are Redefining Software Engineering. This article defines agentic engineering as a multi-agent coordination model where AI agents act as digital team members. The selected source says those agents have defined roles, share memory, and a common observability layer, and they move software through the full delivery pipeline rather than just generating code faster. The article reports pilot results from more than 20 debugging workflows. Coordinated agent execution produced a 93% reduction in time to root cause compared to historical baselines, with more than 20 engineering hours saved across 512 sessions in a single month. It also says development workflows showed a 65% reduction in execution time, with the biggest gains coming from compression, downstream testing, and not code generation. The source distinguishes agentic engineering from AI coding agents like Codex or Claude. Coding agents are described as strong at translating intent into code within a single user-driven session. Agentic engineering is described as higher-level control plane that orchestrates cross-team workflows, maintains long-term memory across agents, and manages state and traceability across the software delivery lifecycle. The source says the two are not competing. Coding agents can run inside worker agents as reasoning and code generation engines. My interpretation is that this is one of the strongest architecture stories in this podcast, because it pushes beyond agent as assistant into agent system as workflow fabric. The reported numbers are source-reported pilot numbers, not independently verified, so we should treat them just as claims. Still, the decomposition is interesting. The biggest gains are attributed to downstream testing compression, not code generation. That matches a pattern many engineering leaders will recognize. Writing code is rarely the only bottleneck. It was never about writing code. Writing code was never the hardest part. Root causing, reproducing, testing, validating, documenting, handing off, and coordinating across teams can dominate cycle time. If a multi-agent system can carry state across those stages, preserve traceability, and coordinate specialized roles, the value is not just faster typing, it is reduced workflow friction. The control plane framing matters. A control plane needs identity, permissions, memory boundaries, observability, escalation paths, and failure modes. Once you have multiple agents interacting across delivery stages, you are designing a distributed system with probabilistic workers. That is not a toy problem. My read is that the future engineering organization will not evaluate agent systems only by lines of code generated. That metric is too narrow, meaningless. The better questions are, did time to root cause shrink? Did test feedback arrive earlier? Did handoffs become clearer? Did the system preserve enough traceability for humans to trust and audit it? If the answer is yes, agentic engineering becomes less about replacing developers and more about redesigning the delivery pipeline around coordinated machine assistance. This next article is truly exciting. It's called AI Coding Agents Get a Stack Overflow of Their Own. It comes from InfoQ News. Basically, what is happening is that Stack Overflow announced a Stack Overflow for agents, described in the source as a beta API first knowledge exchange aimed at AI coding agents rather than human developers. The article says Stack Overflow is trying to close what it calls the ephemeral intelligence gap, where agents repeatedly rediscover the same fixes and patterns in isolation instead of sharing these patterns through a common shared memory. The article describes the product as an API front-end over a curated knowledge base tuned for agents that write and debug code in production environments. The stated intent is for an agent to query a store of verified answers, debugging trails, and patterns before starting costly trial and error. The article quotes the Stack Overflow team saying, "It creates an expensive repetitive reinvention loop that forces millions of independent agents to rediscover the same architectural pattern and bug fixes over and over again." The article also says that the Stack Overflow for agents extends the familiar question and answer model into 3 post types designed for agent workflows. In my eyes, this is a memory architecture story. Today, many coding agents behave like brilliant interns with short-term amnesia. They can solve a problem inside a session, but if the session is not captured somewhere durable, the next agent might repeat the same exploration. Stack Overflow's framing is that a shared, curated, API-accessible knowledge exchange can reduce that repetition. For architects, the key design question is trust. If an agent queries a knowledge base before making changes, what counts as verified? How fresh is the answer? Does the answer apply to this framework version, this dependency graph, this operating system, this internal convention? I think those are the engineering consequences of moving Q&A from humans reading pages to agents consuming knowledge through APIs. There is also a workflow implication. If agents can publish or consume debugging trails, not just final answers, then the useful artifact may be the path, symptoms, failed attempts, environment clues, final fix. That maps nicely to agents traces from earlier stories. The more the ecosystem captures not just outcomes, but trajectories, the more reusable agent experience becomes. My cautious take: a Stack Overflow for agents could reduce repetitive trial and error, but only if curation, provenance, and applicability are first class. Otherwise, it risks becoming a faster way for agents to retrieve stale or mismatched advice. The article emphasizes verified answers, debugging trails, and patterns. So the ambition is clearly curated knowledge. The hard engineering work will be making that knowledge safe enough for automated consumers. The next article is a guest post from Monday.com in the LangChange blog. It's called Monday Service plus Langsmith, Building a Code-First Evaluation Strategy from Day One. The Monday.com guest post says many teams treat evaluation as a last mile check, but Monday made it a day zero requirement. Monday Service is described as an AI native enterprise service management platform designed to automate and resolve inquiries across all service departments. The AI service workforce is described as customizable, role-based AI agents that make ticket load of human representatives. The article shows how Monday.com built an evals-driven development framework to catch AI quality issues before users do. Among the reported achievements we have, evaluation feedback loops became 8.7 times faster, from 162 seconds to 18 seconds. Coverage became comprehensive testing across hundreds of examples in minutes instead of hours. Production traces enabled real-time end-to-end quality monitoring using multi-turn evaluators, and eval logic was managed as version-controlled production code with GitOps-style CI/CD deployment. The article also says the AI service workforce is a customizable, land graph-based React agent designed to automate and resolve inquiries across enterprise services management use cases. My interpretation is that this is perhaps the most operationally concrete eval story in today's podcast. Day zero matters because it changes incentives. If evals arrive after alpha, users find gaps. Evaluations become cleanup. If evals exist from the start, they shape design. The reported speed improvement from 162 seconds to 18 seconds is more than a convenience metric. In deployment systems, feedback's latency changes behavior. If tests take too long, engineers run them less often. If evals are fast enough to fit into normal development, teams are more likely to use them continuously. That is true for classic software and even more important for LLM systems, where small changes can have broad behavioral effects. The code-first part also matters. Managing evaluation logic as version-controlled production code means evals can go through review, CI/CD, rollback, and ownership. Again, I am interpreting from the article's GitOps-style CI/CD language, not adding any claim about their exact repository setup. The architecture point is that evals become part of the software supply chain. The multi-turn production trace detail is important because service agents often fail across conversation state, not just one answer. A ticket resolution agent may ask a clarification question, use context, propose a fix, and follow up. Evaluating only the final message can miss whether the agent took a risky path. End-to-end quality monitoring on production is therefore aligned with the actual user experience. My read is that if you are building customer-facing service agents, day zero evals are not just gold plating. They are risk management. The earlier you define what good behavior means, the easier it is to prevent quality debt from becoming customer-facing debt. And this brings us to the last entry of today's podcast, which is again a line change blog post. And it is called Testing Fine-Tuned Open Source Models in Langsmith. This guest post was written by Ryan Brandt, CTO and co-founder at Chat Open Source, described as a business specialized in enterprise AI chat that runs entirely within an organization's network with no third party needed. The article says open source models are increasingly capable for applications, with examples including Mistral 7B and the Llama 2 family. It compares swapping better models in and out of an application to cartridges in an old game console. It also says fine-tuning different versions increases the number of possible model cartridges a developer might need to compare. The article asks how teams can productionize evaluation so they can choose the best tool for the job. It says Langsmith provides a user interface and API for creating evaluation datasets, and those datasets can be used to run tests on multiple models and compare performance across multiple access. The article says the study began with a goal to fine-tune Llama 2 7B and Llama 2 13B using SQL create context data. My interpretation is that the model cartridge metaphor is useful. It's crucial, actually. It captures both flexibility and danger. And just to understand how relevant this is, just think about Fable 5 and what happens last week. If models are easy to swap, teams might be tempted to swap them casually. But for production systems, every model change is a behavioral change. Fine-tuned variants multiply that surface area. The enterprise context matters too. A system that runs entirely within an organization's network might be motivated by privacy, control, or deployment constraints. And what we can definitely say is that model evaluation becomes especially important when the organizations control the model options and the tuning process itself. Architecturally, this suggests a model evaluation registry pattern. I'm using that as interpretation, not as a source term. Each candidate model should be associated with datasets, test runs, metrics, traces, of course when available, and decision history. Without that, model selection becomes a memory game. Somebody remembers that model A felt better. Maybe it felt better last month, but nobody can reproduce the comparison. The article's multiple access phrase is very important. Model quality is not one-dimensional. A model might be stronger at one task and weaker on another. It might be cheaper, slower, more controllable, or better suited to a domain. The point is simply that production model selection needs a structured comparison, not a single vibe-based score. This closes the loop with our earlier stories. Whether we are talking about agents, data assistants, service workflows, or fine-tune open source models, the production discipline is the same. Capture representative data, run systematic evals, inspect traces or outputs, compare changes, and keep the process close to engineering workflows. So, putting everything together, what do these 10 stories say? Well, a fact recap. LangChain says agent production monitoring is different because inputs are unbounded, behavior is non-deterministic, and quality lives in conversations. OpenAI's data agent presentation emphasizes right data context, memory, and evals, with a source stated 80% of the company directly using the data platform. Microsoft's Windows story frames containment, identity, and manageability at OS-level requirements for agents with the SDK policies, isolation mechanisms, and enterprise management integrations. Dosu's evaluation-driven development story treats evals as a way to understand product changes on their probabilistic behavior. LangChain's agent debugging guide says traces matter because agent failures can be reasoning failures, not stack traces. Langsmith benchmarks emphasize shared datasets, results, and full traces. Cisco's agentic-engineering story frames multi-agent systems as a control plane for software delivery and reports pilot reductions in time to root cause and execution time. Stack Overflow for agents aims to give coding agents a shared, curated knowledge exchange to reduce repeated rediscovery. Mondays.com service shows a day zero code-first eval strategy with faster feedback and production trace monitoring. And the open source model testing story shows why model swapping and fine-tuning require systematic comparison. My interpretation is that the agent stack is becoming an operations stack. The center of gravity is moving from can the model do the task once to can the organization observe, evaluate, secure, compare, and improve the behavior over time? That means the winning teams are probably not just the ones with the cleverest prompt. They are the ones that build the boring, durable machinery around the prompt. Traces, eval datasets, policy boundaries, memory systems, benchmark disciplines, model comparison workflows, and human review loops. Boring is the best way. I always say boring is great, boring is good. The right kind of boring, right? Boring like bridges that do not fall down. And there is a cultural shift here too. Engineers need to get comfortable treating conversations, traces, and failed agent runs as first-class artifacts, not as noise, not as an embarrassment, but as the raw material of reliability. If I had to compress today's podcast into one architectural sentence, it will be this. Production agents are not features you ship once. They are systems you continuously govern. That's it for today's Arturo's Engineering Solo. Thanks for hanging out. Keep your traces rich, your evals close to the code, your permissions tight, and your claims source grounded. Nos vemos. Oh, yes, please. If you like the podcast, please remember to like and subscribe. Bye.